All right, this is our last test, and this is the root test, and you can see it's very similar to the ratio test that we did before. So what we do is we take the nth root of it, and it's that same basic idea. We're trying to find out what that term is here. And so if L is less than 1, it's absolutely convergent. L is greater than 1, its series is divergent, and at 1, it's inconclusive. So let's try some. So we're going to take the root, and you can see when we use this root test, you take the root, put an absolute value around it, like that. So if we take the nth root, it cancels that in. So the absolute value is here, like that, but you can just get rid of the n. So we end up with 1 minus n, 2 plus 3n. Now, here's where we know n is greater than or equal to 1 here. And so what we do is we just do a little modification. If you say n minus 1, and I'm going to put the 3n in front as well, just because all the n's are in front that way. It'll help with our limit. But if we put the n in front, now when we subtract them, this is going to come out positive, and that's what we want with the absolute value. So now when we do our limit, as n approaches infinity, we can just use the n minus 1 over 3n plus 2, and obviously that's 1/3. And that's less than 1, so just like before, if it's less than 1, it's absolutely convergent. So our series is absolutely convergent. So they're nice and quick. It's a good thing to use. So if you see that power of n. All right, so let's try another one. So power of n, like that. And again, this would just become, and there you go. Now, obviously n is greater than 1, or 2 here, sorry. Yeah, because 1 would not be good at the denominator, right? That would give us 0. So greater than 2, and we're going to get everything working out nice. So n over ln of n would be positive. Natural log goes off to infinity after that. And so now when we do the limit, as n approaches infinity of n over ln of n, you start to go, okay, now what? Well, if you look at this, this goes off to infinity. So if we rewrite it, I like x. So limit as n approaches infinity of x over ln of x, you can see, not n, x. There we go. You can see that this goes to infinity and this goes to infinity, meaning we can use L'Hopital's rule. So this would be a limit as x goes to infinity of 1 and 1 over x, which is the limit as x goes to infinity of x, which is infinity greater than 1. Therefore, the series is divergent. So there's one divergent and there is one convergent for you. Now there is a limit of n to the n to the 1 over n that we've done a long time ago that I thought I would throw it in because these do pop up here with root tests. So just remember that one. If you see n to the 1 over n, it equals 1. It'll help. Okay. So why? So why are these convergent? Well, let's look at it this way. So we're saying that if RL, which we can now say is R, see where I'm going with this, is less than 1. So if this limit is less than 1, we're saying it is convergent. So if this is less than 1, right, we have our R is less than 1 then as well. We can write it this way. So then we can say that this a sub n then has to be less than R with the root. And if we rewrite that, we would get the absolute value of a sub n is less than R to the n. Well, when we see series like that, we already know that if R is less than 1, that this series converges. And then you can use the comparison test to say, well, if R converges and this is less than R, well, then it has to converge as well by the comparison test. So we're using that whole ratio thing again. So that is why these things apply. The root test applies just like the ratio test does, and just like the geometric series do.